Okay, today we're going to expand binomials, and this means raise a binomial, something plus or minus something, to a power. So far, the second power is what we've seen. We had a shortcut for that, right? Like if we have, for example,
first two multiply the last two, and then the
yeah, so like if I have x plus 3 to the second power, that's just x squared plus 6x plus 9, right? We square the first, we square the last, we double the product of the two. Okay, so 3x double to 6x, that's middle term, right? So that's our shortcut for that. What I want to do today is I want to come up with a shortcut for a plus b to any power. And it comes down to what's called Pascal's triangle right here. This is Pascal's triangle. And Pascal's triangle is easy to create. One's on the outside. And then to get every other number, you just add up the two numbers above it. So 1 and 3 make 4. Let's say 70 and 56 make 126. 6 and 15 make 21. 6 and 4 make 10. 2 and 1 make 3. We all see that? Just one's on the outside. Each next row has an extra number in it. So basically, it kind of goes like this. You start with 1, 1, 1. 1's on the outside, 1 plus 1 is 2. 1's on the outside, 1 plus 2 is 3. 1 plus 2 is 3. 1's on the outside, 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Like so. Just keep on going down as far as you need to go. And with that in mind, this row right here represents the power we're doing.
whoa.
Okay, we'll call that the power row for lack of a better name. So if I'm doing the second power, I use this row, third power of this row, sixth power of that row, 10th power of this row, and so on. Every row of numbers. And let's say I'm doing, for example, problem number 1, which is x plus 3 to the third power, right? So I would pick this row right here, because it's the third power, 1, 3, 3, 1. And this is simply how to construct the terms, and it's not nearly as confusing as it looks. PT number plus a to the nth plus r times b to the 0. So this times this times this. PT number is the number from Pascal's triangle. A is the first object raised to whatever that power is. B is the second object raised to the 0 power. The next number, or the next term, always put plus. The next one is going to be Pascal's triangle number, the next number, which would be 3. And then you drop the power of the first by 1, you raise the power of the second by 1. Next Pascal number, drop by 2, raise by 2, and so on, until you get all the terms. So let me just demonstrate using Pascal's triangle on this problem here. So again, first off, if you don't have the 3 memorized yet, just build Pascal's triangle down and you get the 3. It's 1, 3, 3, 1. And each term is built by a Pascal number, a letter to a power, or a letter or number to a power, like that. So the first number is 1. So my first term is going to be 1. Then I take x and 3. It's positive x and positive 3, right? And the first powers are, the first object gets raised to whatever the highest power is. The second object gets raised to the 0 power. That's how you construct the first term. 1 is the Pascal number. X is the first object, 3 is the second object. The second number in Pascal is 3, so I put plus 3. And then, again, my objects are x and 3. And this is 3, so it reduces by 1. This is 0, increases by 1.
If you say that one again, I don't understand that.
X and 3 are the pieces.
Yeah.
3, 0. That decreases by 1, that increases by 1, use the next Pascal number. Alright? Next number is 3, so plus 3. And my pieces again are x and 3. You always put the exact same things in these parentheses every time. Cubed, squared, first, 0, first, second. So the first object is always counting down by 1, the second object is always counting up by 1. And the last number of Pascal is 1. X and 3, x, 3, 2, 1, 0, 3 to the 0, 1, 2, 3. So each piece is created by the Pascal numbers along with the pieces in the problem raised to whatever powers they're supposed to be raised to. What's left to do then is to simplify the entire expression completely as much as possible. This becomes x cubed. 1 is 1, 3 to the 0 is 1, x cubed is x cubed, 1 times x cubed is x cubed. This one, 3 times 3 is 9, x is squared. This one, 3 times 9 is 27 times x to the first. And this one here, 1 times 27 times 1 is 27. And that is the product of the binomial, the expansion of the binomial, if you will. Okay. You will find that cubic functions might be just as quick just to do by hand, but 5th power functions aren't. 10th power functions aren't. 25th power functions, I pray to God you never get one of those, but they would not be. Do a 25th power function by hand, you're going to be looking at 4 sheets of paper and a spare case of radish crayon. Where Pascal's triangle would take just a longer amount of space, but it would take this much to do. So let me just real quick, just so we're on the subject, let's suppose we had one a little bit uglier. X minus 2 to the 5th power, let's say.
Is that
1, 5, 10,
5,
10.
yeah.
And you don't have to draw the entire triangle out. If you can remember any row, you can use that to get the next row down. So let's say I don't remember the 5 row, because of course you just got it. But if I know that 1, 3, 3, 1, what we just did, then 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. This will be the row I'm going to use. Okay? And again, I use it because the second number represents the power. It should match that. Or 1, 2, 3, 4, 5, 6 terms is 1 more than 5. All right?
So you're, okay, sorry.
Go ahead.
So your power is which one you choose for the thingy?
Whatever this number is should match the second number.
Okay.
That'll be the right row.
Okay.
Or the number of numbers in the row, which is 6 of them. See, there's 6 numbers there. It should always be 1 more than that power.
Okay.
All right? Whichever way you want to look at it, both those things always happen.
Okay.
All right, so if I'm constructing the terms, the first object here is x, the second object is -2, and notice that's -2. Pascal's triangle on that sheet that I just gave you has an a plus b to the nth power. Plus means whatever sign you have is what you have, so we have a -2. So if I'm constructing the terms here, 1 x to the 5th, -2 to the 0. Plus 5 x to the 4th, -2 to the 1st. Plus 10 x to the 3rd, -2 squared. Plus 10 x squared, -2 cubed. Plus 5 x to the 1st, -2 to the 4th. Plus 1 x to the 0, -2 to the 5th. That's how long it takes to write it down when you get good at it. All I'm doing is taking a number off of that. First object to the highest, second object to the lowest. 5 is the highest, 0 is always the lowest. X is counting down 5, 4, 3, 2, 1, 0. -2 is counting up 0, 1, 2, 3, 4, 5. And the power of the numbers 1, 5, 10, 10, 5, 1 are the numbers coming off of Pascal's triangle. 1 times x to the 5th. -2. Ahead of myself there. -2 times 5 is -10 x to the 4th. So if minuses show up in the problem, minus is going to show up in your answer. There's only pluses using the Pascal's triangle technique, but odd powers of a negative number create negative numbers, right? 4 times 10, that's positive. 4 times 10 is positive 40x cubed. This will be -8 times 10 is -80x squared. This will be positive 16 times 5 is 80x. And that's -32 times 1 times 1 is -32. And just like that, that's x minus 2 to the 5th power. Okay, that's how much space Pascal's triangle takes. What?
What was the last one?
-32 times 1 times 1. That's
Oh,
x to the
okay,
0 power right there.
Okay.
Alright? So no matter what the expansion you have to do is, if you're going to use Pascal's triangle, that's how much space it takes. The bigger the power, the longer that expression is, but again, it's just create each term, simplify each term, and you're done. So it is a very good shortcut. It's one that you need to practice with the easy ones, and then you'll have that in your wheelhouse when it comes to the uglier ones.